Okay, hi everybody. My name is Mansour Khusravi. I am reservoir geologist. I work with Illinois State Geological Survey as a reservoir geologist. And in this webinar, I wanted to give you just a short presentation about the concept of reservoir modeling and what actually the goal of this presentation is how we can create a reservoir model and actually the fundamental behind that. So let's go to first slide. Okay, that's as a reservoir geologist, actually you should be able to be familiar with several different subjects. For example, you should be able to be familiar with sedimentology, with interpretation of the positional environment, not in detail, but you should be familiar with those terms and you know what to do. Actually, the workflow needs different output from different subjects. For example, seismic interpretation. Why do you need seismic interpretation? Actually, after seismic interpretation, they give you, a geophysicist give you some horizon. After that, you should be able to import those horizon and adjust them with well data. Why do you need some sort of, for example, depositional environment? Interpretation of the depositional environment, because you wanted to import those as a trend. For example, look at this image at this part. If you know that, for example, this is a channel and you have turbidite here, you can better model your porosity, because in this channel you have some sort of sediment with high porosity and better permeability than sediments in those areas around this channel. So you should be able to be familiar with that. Also, you need some sort of data from petrophysicists, same as water saturation, same as porosity, permeability data. And actually, you should be able to work with a reservoir engineer, because you can send up them a model, a static model, and after that they your model, they history match your model, they import the well test data, but after that they get back to you again and you should modify the model based on their findings. Maybe they find something same as faults based on pressure data, and you should look at again, review and revisit again your model, and after that modify your model and update your model. So you need to work with these different subject, and after that update your model. And so the actually as a reservoir geologist or just geomodeler, it doesn't mean that you work alone. You should work with a different engineer in your company, in your firm, to have a very good model. Okay, let's look at this.
Mr. Mansour,
Yes.
sorry for interrupting you. Could we have a full screen of your presentation? Because we have one and another one by the side. So if it's possible to get a full screen.
Let me just stop sharing, and because I have two monitors, let me stop sharing, and after that disconnect one of them.
Okay.
Let me stop share. How about now? You can see it full screen?
Yes, yes. Now I can see full screen.
Okay,
Thanks a lot, and sorry for interrupting. You can
no
continue.
problem.
Okay.
Sorry about that. So why we actually, our preference is 3D model instead of 2D model. You know that, for example, 30 years ago, 40 years ago, if you look at the publication, you just see a 2D models. And you see, for example, let me change it to this one to a pen. Okay, in the past, if you see the publication, they have just, for example, porosity model. And after that, they mentioned that, for example, what's the initial oil in place based on this porosity, this, for example, uh, this reservoir. So actually for volume, look at this image. For volume, if you wanted to calculate the volume of reservoir, you need the area of the reservoir. Also, you need the H, that's the thickness of reservoir, the porosity, and the water saturation, or the oil saturation versus BO. That's oil formation volume factor. In the past, because they didn't have this type of softwares, so they use just a 2D model. They have, for example, the area of the reservoir, and after that, they have the thickness of the reservoir at the well. So they have the thickness, they have the area, and also they mention that, for example, the uh, average phi or porosity is 30%, and after that, what's the volume of the reservoir? What's the oil in place of the reservoir? But about 20 years ago, we uh, we had very good, for example, reservoir modeling software, same as Petrol, same as Roxar softwares, that's reservoir modeling software. And with those software, you can visualize better the spatial relation of the porosity, permeability, water saturation. Also, in this 2D map, you cannot be able to map the faults. But with this software, with this new software, you can model the very complex structures and faults. And for example, some faults reduce the volume of reservoir, some faults increase the volume of reservoir, or you can import the properties same as porosity, permeability. You can find the trend of them. You can find the heterogeneity of the reservoir, and you can give a better static model as an output for better history match to the reservoir geologist. But the result, you can see that the result will be the same. The concept is the same. You need the A, the area of the reservoir. You need the H, the thickness of reservoir, and you need the phi. So the concept is the same, but you can, with the 3D models, you can better, you can have a better static model with better accuracy. So let's look at at first, let's look at the depositional environment, the data you needed for reservoir. For example, at first you should know that the reservoir is a carbonate or is a siliciclastic reservoir. And if you have a carbonate reservoir, what's the depositional environment? Because we have different type of depositional environment. For example, look at this depositional environment. In this part, you have shoal facies, but sometimes you have reef. You have reef instead of these shoal facies, and sometimes in this area also you have shoal facies in the tidal flat area or lower intertidal. You have these shoal facies. They are a very good reservoir. Sometimes you have calciturbidite in this area. So the in some places, same as here, you have just shale, but if you have a high slope of this area, you will have a calciturbidite, same as turbidite in siliciclastic, and they are very good reservoirs. So you should know the type of depositional environment. Look at this turbidite depositional environment. In this area, you have channel system. And in this channel system, for example, in the higher parts, you have some sand with high porosity. Also in this area, you have sands, but maybe the grain size is lower than this part. Also, but in this area, you have shell. I remember that I worked for, as a well site geologist, I worked for an offshore oil company, and we have this type of environment on that area. When we drill, for example, one well in this site, we have a good production, but in close to that well, when we drilled a well in this area, we have a very bad actually production. So it's very important to know the trend of the sediments, or the trend of the properties, and also know the type of the positional environment. Look at this also, this fluvial and delta environment, the positional environment. For example, in this delta, you have alluvial system in this area. You have very coarse sediments in this area, but because they are very close to source, you have very bad properties here, because you, actually you have, for example, sandstone with very fine grain that fill the porosities. But in this area, when you have a braided river, you have very good porosity. When we go near the actually sea, the size of sediments decrease, and in this area you have the finest sediments, or also in this area. So look at also the delta. In the delta front, you have a very good sediments, but in the pro-delta, you have very fine sediments. So it's very important to know that. Also look at this area. If you have a well here, if you drill the well here, because you have very coarse sediments here, maybe you have a better porosity. But if you drill the well here, you have a bad property. So it's important as a reservoir geomodeler, or as a reservoir geologist, it's very important to have a good zonation. In the past, the zonation was based on just lithology. For example, they connect the sandstone in different wells together, or they connect the shale together. But right now, most of the companies use the sequence stratigraphy for zonation. Why do you need zonation? Because you wanted to create a framework for your reservoirs. At first, you must create a framework. After that, adjust the faults, import the faults, adjust the surfaces with faults, and create the grids, distribute the properties, and finally, you have a geocellular model. Let me show you what is the difference of different type of zonation. For example, let's look at these 4 wells here. You have 4 wells, and in this well you have sandstone. Again, you have sandstone here, and again in this well you can sandstone. If you wanted to have a zonation based on just lithostratigraphy, you connect this sandstone together. For example, zone 1 is the top of this sandstone, and the base is the base of this sandstone. And if you have shale, you connect those shales together. If you have, for example, siltstone, you connect those together. So, but in the reality, they are not look like the type of the stacking pattern of the sediment is it's not look like this. For example, let me show you with a pen. Okay, imagine that we have a delta here, and this is C. Okay, and this is C. When you have a delta here and delta deposit the sediments here, you have very coarse grain here and shale in the perdelta, okay? Again, when the sea retrogrades, the delta again deposit the sediments here. You have coarse grain here and shale here. Again, the delta goes toward the sea, and you have sediments here, shale here. So if you have 2 wells here and here, based on lithostratigraphy, you have sandstone here and also sandstone here. So you connect the sandstone of this part to this part, but that's not connect because they are for different times. So in the sequence stratigraphy, they recognize these surfaces as, for example, high stand system track, low stand system track, transgressive system track. And after that, give you these tops as a top of the zone, not these tops. And they connect the shell together. So they give you this type, and they create your flow units, because these flow units, if you have hydrocarbon here, it actually move in this part, not moving in this part. So they give you these surfaces. They are time surfaces. So right now, look at this one. This sandstone is connected to this sandstone. For example, this three sandstone connected to 2, connected to 1, not this sandstone connected to this sandstone in this part. So this zonation is based on sequence stratigraphy. The sedimentologists give you this top of zones, and after that you import these zones and you create your horizon based on these tops in the reservoir modeling software. So after that, you can distribute the properties, and you say that, for example, I have sandstone that pinch out in this area, and it's not connected to this sandstone, but the lithostratigraphy give you the surfaces like this. For example, for this one gives you this surface, or maybe this surface. That's a wrong interpretation. So be careful about that. Okay, so that's the sequence stratigraphy. Sometimes based on the seismic attribute, you can find your the surfaces, especially the unconformity. You can see those in 2D or 3D seismics. So you have those surfaces. Also based on This, for example, top lap, on lap, and down lap, you can find those surfaces, and after that import those as a horizon into your reservoir modeling software. So again, this is when, for example, someone say that this is the layer cake zonation, it means that in well A, you have 3 wells here, you have shale here, sandstone here, again, shale and sandstone. You just in the lithostratigraphy, you just connected the surfaces or the interval based on lithostratigraphy. For example, in this well, you have shale, you connect them based on shale and also the sandstone, but that's not correct. But look at the zonation based on sequence stratigraphy and system track. You can see they are actually, they pinch out in this part, in the eastern part, and also in the western part. So that's the new type of zonation. Also as a reservoir geomodeler, you should know about the type of diagenesis. What is the diagenesis? The diagenesis is the physical and chemical changes after deposition of sediments. So this type of diagenesis processes are important. For example, dissolution, compaction, cementation, and dolomitization. They are important. We have different kind of diagenesis, different other type of diagenesis. For example, recrystallizations, micritizations, but they are not as important as these 4 processes. For example, if you have dissolutions, you maybe have a better permeability. You have porosity, but you maybe have a better permeability because it depends the pores connected or not connected. If you have a compaction, it decreases the reservoir quality. If you have a cementation, again, it decreases the property of the reservoir. And if you have a dolomitization, maybe you have a better quality or better porosity and permeability. Let's look at this, for example, type of dissolution. We have different type of porosities. For example, you have in the carbonate, you have interparticle, intraparticle, or intercrystal. Especially in dolomite, you have this moldic, fenestral, and shelter or growth framework. But in the sandstone, most of the time you have intergranular porosities. But similar to that, you have interparticle in carbonate. Also, you have different type of porosity that are not fabric selective. For example, fracture, channel, vogs, and cavern. So in Iran, I remember that one of the very good reservoir was Osmari formation. This formation doesn't have, if you look at the thin sections, you can't see any porosity. But because of the fractures, they have a very, very high permeability. So maybe in the thin section, you can see very good porosities, but in the reality, you can have a high permeability. But let's look at some of the thin section. For example, this cementation, look at this oid grainstone. There are oids in the carbonate, and look at this cement around them. You can see that actually the reservoir quality decrease or porosity decrease because of this cementation. They fill out all of the spaces between the oids. The oids, when you have oid, it means that you are in the high energy environment. You should see the porosity and also permeability. But look at this thin section, and because of the cementation, you don't have a very good porosity. And look at this sandstone. At first you had intergranular porosity, but because of the carbonate cementation, you can see, if you, for example, if you test this, analyze this core interval, maybe the porosity is less than 2 or 1%. But look at this thin section. This is dolomite. You can see the rhombs of dolomites here, and you can see that we have a very large intercrystalline porosity. Also, in this sandstone, you can see the intergranular porosity, and they are connected to each other. So you have a good, very good porosity and permeability. And again, you look at these rhombs of dolomite. You can see two type of porosity, intercrystalline porosity. In this part, you can see these very fine porosities. Also, they are connected to each other, and maybe they are vogues, or maybe they are, because most of the dolomitization are secondary dolomites. They first were limestone, and they come based on diagenesis processes. This sediment convert to dolomite, and maybe they are shadow of some sort of carbonate, or maybe you have, at first you have a voggy porosity, and after that you have this type of dolomitization, and so they connected to each other. Look at this one. So you should have a very good permeability. And this is also, you can see some moldy porosities here, and some sort of, maybe, yeah, in this part you can see voggy porosities. They are very connected, and this sample should have a very good permeability. As I mentioned, that the compaction reduced the porosity and permeability. Look at this compaction here between these two voids, and or this one, actually, because of this compaction, and also cementation. Look at this cementation here. It reduces the porosity. And look at this stylolith here, and this is dolostone. But because of the compaction, it reduces the porosity and permeability very high. So that was a very brief presentation about slides about the type of porosity and porosity we have mostly in the carbonates. But let's get back to the static model. For a static model, you need some sort of structural maps. At first, this structural map maybe comes from the sedimentologists, maybe comes from the geophysicists, but you need those surfaces to start your work for creating a static model. So at first, you must import the wells. The wells, for example, you work for, you wanted to create a static model with an oil, for an oil field with 100 wells. You must at first import the wells, wellheads, and also the top of the formation. For example, you have a field with the different wellheads. So you must import these wellheads at first, the survey of those wells, the top formation, tops of those formation. After that, you must import the structural map. This structural map, maybe it came from the geophysicist based on seismic interpretation, or maybe you don't have any seismic data. So based on the well tops, you must create a surface. So in some of the very oil field, you have also, they say that they are underground contour maps. Maybe they have the underground contour map and you can digitize them and import them into the software. Also, that's the type of 2D map. But and also sometimes you create an isopac map and also isopac map based on just the thickness of the reservoir. They're also the type of 2D maps. Sometimes the sedimentologists give based on the positional environment interpretation, they give you some sort of trend maps. And also, for example, he or she gives you a trend map about where the porosity goes up and where the porosity goes down. So that's this type of maps. Also, you should have some sort of deep azimuth and deep angle. I will show you in next slide this type of also the maps for the static model. Let me show you some of them. For example, the first one is the structure map. The structure map is type of subsurface map that have the elevation of the interval in subsea. So maybe you should create one of them into the software based on well tops. And if you have the result of, for example, correlation of the chart, maybe a sedimentologist or geologist give you this type of map and you can import it in your software. Let me show, okay, that's the 2D, okay. Let me show you the thickness map also. This is the type of thickness map. This thickness map actually show the thickness of each interval or each zone. I mentioned that in the previous slide that you should get the top of the zone from geologists and you import those, and after that, based on the thickness of this interval, you can create this 2D map for the thickness of reservoir, or thickness of the intervals. How we can create those, let me show you. Okay, if you have a well here, for example, it's in the onshore, you have the logs and also based on the measure depth. So you must import the wellhead of this well, and after that KB, that's Kelly bushing elevation. And after that, based on these, you can calculate the true vertical depth of the that's true vertical depth of the intervals. So in this part, when you have, for example, a bed or interval look like this, and based on log, you have the depth of this interval, but you must create two type of other map. One of them is isocore. You have the thickness of this one. You have also the survey of this well. You have the inclination based on your zonation. You have the inclination or a slope of this interval. After that, in your software, you must create this type of thickness map. For example, isocore. When we say isocore, it means that this is the true vertical depth. From here, if you have, for example, you have a well that have a have a through its vertical, it's the depth from here to this part. But the true vertical thickness of the reservoir is here. So if you create the map based on true vertical thickness, it's isopac. And if you create a map, a 2D map based on true vertical thickness, or TVT, is isocore. So you can create two types of thickness map, isocore and isopac maps. After that, you can create this type of 2D maps, or maybe 3D. In the software, you have this type of maps you can create for each one. But sometimes a geologist he can provide you by hand, or for example, based on interpretation of the depositional environment, he can give you a map look like this, for example, just by hand. For example, let me show you. For example, you have a channel system here, and he just give you some contours. For example, in this part, we have a very good sandstone with high porosity and permeability. In this part, medium porosity or fair porosity, permeability, and low, in this part, low porosity, low permeability. He or she can give you some sort of this type of map, and after that, you can digitize them and import them into your software as a proxy for, or as a trend to helping you better model the porosity or permeability, your permeability. So if you look at, for example, these four maps, you can see in this area we have high porosity for this interval. Also in this area you have high porosity. In this area you have high porosity. But for this interval, it's very low porosity here. If you, for example, if you drill a well, look like this, that's a deviated well. You have a very bad porosity for this interval. But for this interval, you can see you have a very good porosity. Okay, the other type of the 2D or 3D map are deep angle and deep azimuth maps. This type of map give you the deep and azimuth of the interval or horizons. For example, let me show you in this picture. That's a deep angle map of this surface. That's a structural surface with this drilled well in almost everywhere of this horizon. But you look at this, this is deep angle based on this interval. And you can see most of these parts is actually less than 2 degrees. But the deep are less than 2 degrees. But you can see that in this part, you have very warm color here, 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 in this part, in this part. Actually, look at this part. Look at this part here. That's the deep angle of this area. So it shows that in this area, maybe you have a monocline, maybe you have a very large fault also in this area. This area shows that this area is a faulted area. Also in deep azimuth, shows the azimuth of this horizon, and it helps you to find better the actually the faults and also the deep and azimuth of these intervals. So right now, what is the 3D model? The 3D model represents the physical space of the reservoir by discrete cells. For example, you have a reservoir, 2D reservoir. Right now, you wanted to create a discrete cells or grids. Why? Because you wanted to assign some porosity and permeability to these cells. So, or water saturation. So our intent to create those 3D model is to create this type of cells. So because of that, we say that this is a geocellular model, because we wanted to create cells. In this actually surfaces, you don't have any cells. You have just surface. But for reservoir modeling, you need actually discretes based on those horizons. For example, you have some sort of horizon, you have your zones, intervals. After that, you divide them to layers and also divide them into some sort of grids. So after that, you assign number you assign porosity and permeability to these cells to calculate the volume of the reservoir. You calculate the oiling price of the reservoir, or whatever you wanted to calculate. For example, pore volume of the reservoir, or something like that. So for creating this 3D model, at first you must create a stratigraphic framework. After that, a structural framework, facies model, and property model. Let me show you in next slide. For constructing a stratigraphic framework, at first you need the horizons. You need horizon from seismic data, or as I mentioned that you need to create if you don't have the horizon from seismic data, you must have the well data to create the horizon. For example, if you have a horizon, the geophysicists give you some sort of horizon, for example, horizon 1 and horizon C, because it has a very good reflector in seismic interpretation, and he or she gives you these two type of horizon. After that, you have some wells with well tops, so you must adjust this horizon with these well tops, because what is important, more important, is the well top, because you have it in the reality. You have it because the drilled actually penetrate this formation at this step. So you adjust the horizon with well tops. But in other places, you trust the seismic data. Sometimes you don't have the seismic data and you just have wells with well tops. So with software, you, based on just this well top, you interpolate and extrapolate these well tops and create your horizon. Sometimes, as I mentioned, you have both. Okay, so that's also, it shows that that's a interpretation from 2D or 3D seismic data. You have some sort of, for example, reflectors. Based on these reflectors, the geophysicists give you this horizon and you can import them into your software. But I have it here. Okay, sometimes you have a very good reflector. For example, in this part, you have a very good reflector, or maybe in this part, you have a very good reflector, but you have a different formation with different properties at the middle part, okay? For example, imagine that you have dolomite, you have sandstone here, you have dolomite here, so you have a very good reflector here. But when you have a same lithology, you don't have a very good reflectors. So but this one is reservoir, this part is not reservoir. So you must actually, for a stratigraphic framework, you must create some subzones for your interval. But the seismic interpretation just give you these two horizons, same as this. So because of that, it mentioned that you have interpreted surface. So you have this surface from seismic and also this surface, but you don't have these surfaces. So you must calculate the isopac or isocores, and after that, you create these surfaces. Sometimes just based on well tops, you create them. If you just based on well top, you create them. And whenever you look at surface, most of the time you have intersect with those horizon have intersect with the with your interpreted surface data. So that's not very good. When you create your grids, actually you have not a very good grids. So it's better to look like this. You at first you create these surfaces, these two surfaces from seismic data. After that, based on creating zone, you have this type of workflow. For example, in the petrol, you can create zones based on isopac maps. And after that, you have a very good grids and also uh, without any intersect between the horizon, because you have the thickness of this part. But if you don't uh, import the grids and just based on the well tops, you create them in some places when you don't have the uh, well entry points, maybe they intersect with the upper layer or lower layer. So let's look at this one. Yes. So for constructing a structural framework, you must import your faults because based on seismic data, or sometimes based on, for example, if you have, uh, you look at the logs. If you have some, for example, if you see a repeat of the formation, for example, you have this type of log again at the upper part, you see this being repeated. So maybe you have a fault here, or sometimes a part of, for example, you have this one in a one well, but in closed well or nearby well, you don't have it. Maybe it shows that you have a fault here. But most of the time, based on seismic interpretation, they give you the surface, the faults as a surface or as a line. And you should import those lines, for example, these lines of the faults. And after that, you must adjust. You must adjust again the surfaces with these faults. So maybe because of this fault, they reduce or increase the volume of reservoir. So this part actually, you will done this part in the structural framework part of the software. Same as this one, for example, in this surface, we can, based on seismic interpretation, we have seen these faults, and after that, you can see they are the offset of the faults here, and you can adjust the surface, your initial surface with this fault and also with their displacement or offsets. And you will done this type of structural workflow for all of the horizon, or for all of the horizon that affected by those faults. Okay, the next step after structural framework is pillar grading. In the pillar grading, you create the grid of the or you create a skeleton of the grids. For example, let me show you. Yeah. For example, you have you have a reservoir, and it creates based on the dimension of this grid. You actually can insert those dimension into the software. For example, you wanted each grid 200 feet by 200 feet or 1000 feet by 1000 feet. But after that, you create this skeleton for the framework. And in this skeleton, that's the top of the skeleton, and this is the base. And based on the surfaces, right now, the surfaces change to this type of grids. After that, you have just grids. You have just grid, and you can, with next procedure, you can insert the porosity and permeability or whatever property you have. So in the Scala process, because, for example, when you have a log data, you have a property, for example, porosity, permeability in, for example, half a foot interval. But if you have a layering as, for example, 3 foot, if it's 3 foot, and you have a 0.5 feet interval in the raw data, you have a data as a log, you must insert those into each grid. For example, this, if the thickness is 3 feet, so, and the raw data is just for 5 feet, so you must average them, and you must average them and actually assign this value to each cell. So this process will be done in a Scala process. So in the Scala process, for example, this one, you have the log data for half foot interval. You must assign them, average them, and assign them to the cells for each of them. After that, for each grid of this well, look at, for example, after this process, you have, if you have, for example, 20 wells, you have 20 wells with a scale of data. But right now, in the middle of the wells, you don't have any data. Just in the well, same as this one, that's a deviated well. And in this part, or in this part, if you have a well here, in this part, you have the data. But in this part, you don't have any data. Right now, you have the scale of data. Let's look at the other part. Okay, in the property modeling, you should interpolate or extrapolate the data between the wells. I will show you in next slides. So also based on sedimental study, you can create a facies model, especially when you have a 3D seismic data for siliciclastic. They can give you some sort of bodies, and these bodies, for example, they give you the body of channel, and you can import them. This part help you to better model the porosity and permeability, because if you have, for example, channel system, you use them as a secondary porosity. You import them as a secondary porosity. For example, you wanted to model the porosity. You use this one as a secondary property and model the porosity based on that. So when we say This is object-based model. It means that you have these bodies. If you don't have, most of the time you don't have this. So just based on some trend from the sedimentologists or based on some sort of geostatistical algorithm, you must model the porosity. So when you don't have this one, instead of object-based modeling, we say that this is pixel-based modeling. So if you don't have it, so we can actually use the some sort of geostatistical algorithms to distribute the properties. How? So imagine that we have a channel here. Let me at first give you a concept about that. Imagine that we have a channel system here. And if you look at this one, we have shale here. We have again shale here, and we have sandstone here. And if you look at this one, for example, this channel system, we have sandstone with good porosity here. But if we go through the center of the channel toward the edge of the channel, you can see the property goes down very fast. But along this channel, the property is the same. In the geostatistic, we wanted to find out in which area this property are similar, in which space or in which distance this area we have this similarity. So in the geostatistic, we are looking for similarity and dissimilarity. So if we have this one, for example, if we find out in this direction, we have high similarity, that's a major range of us in the variograms. That's a major. And if the similarity go reduced very fast, that's the actually the minor range, or in the variograms, that's the minor, actually it shows the minor graph of us. So look at this one. It has, we have a channel system here, and in three different, look at, for example, let me show you, that's a well here. We have a real well here. And in this part, we have minor range. Why? Because we have the similarity goes down very fast, but along this one, we have a major range because they are very similar in a very long distance. So in the variogram or geostatistic, we wanted to analyze data, organize the data, and after that find the major, minor, and also vertical range. What is the vertical range? In the well data, we look at the data, we analyze the data to see in which part the properties are similar and in which part they are not similar. So we will find those three variables, and based on those variables, we can model the properties between the wells. So for the geostatistic, we must create the variograms for porosity, variograms for permeability. Assume that in this part, we have a scale of data of porosity and permeability. And after that, based on these variograms, for example, in this part, this is one variogram. It shows that in this part, this is the distance, and this is the variation or semi-variogram of the properties. For example, porosity. It means that in this part, when we reach to seal, It means that in this range or in this part, we have similarity. So we actually write down this range. This is one of our range or one of the minor or major ranges. Again, in another direction, we'll look at the properties. For example, in this part, this another range. So the higher range, for example, in this part, we see similarity. In this part, when we reach the seal, there is no similarity between the variables. So in this part, we write down these major and minor ranges. And because this one is higher than this one, so this is major and this is minor. And also in the well, we can analyze the data to find out the vertical ranges. Based on this variogram and geostatistical algorithms, we distribute the properties. For example, look at this one. This is based on a stochastic simulation. You can see we have different type of, for example, porosity, but this is just based, that's a Kriging algorithm. That's a type of deterministic algorithms. And it just uses the variogram, not histogram. So in this part, you can see that the properties, it distributed the properties and better shows the, for example, the depositional environment. But whenever you use a deterministic model, it actually shows very a smooth model, and maybe it doesn't represent the model. Look at, for example, this one. For example, this one, this is based on Kriging. This is deterministic method. In the deterministic method, if you have a very high number of wells, you can use this one, and it gives you very smooth surface or a smooth model. But look at, this is the reality. Let me show you. This is the reality. You have this reservoir in the reality. But if you use the deterministic method, in some parts, it underestimates the property, and in some part, it overestimates the properties. But when you use the stochastic simulation method, because of different realizations, it gives you better result. It gives you, so if you have low number of wells, or if you not work with very high numbers, it's better to use this type of algorithms to create a model, because it gives you different realization, and based on your different realization, you can make a decision about it. Okay, finally, based on this method, for example, you calculated the area. You have the area based on those surfaces. You have the thickness. You model the porosity, and also based on petrophysical evaluation, you have the water saturation, and also based on reservoir engineering output, you have the BO, or formation factor. You can calculate the stack tank oil in place of the reservoir. That's all of the concept of the reservoir modeling. So that's not difficult, but you should learn very different subject. You should work with different areas. For example, you should collaborate with, for example, petrophysicists, reservoir engineers, sedimentologists, geologists, to have a better model with better accuracy. That's all of my slide right now. If you have any question, that's time for question you can ask. I don't know how much time we have, but okay, Mr. Islam.
Yes, I'm here. Thank you so much for this informative session. It's really amazing and interesting, actually. So, guys, it's time for question. If you have any question, please type it in the chat area, and I will read it to Mr. Mansour so that you can get your answer. I have already a question from Mohammed. He's asking, can he choose a different upscale method for the same type log, depending on the well location in the reservoir?
Yeah, for actually for porosity, yeah, we have different averaging method for upscaling or a scale of the data. For example, based on experience for porosity, we use the arithmetic averaging method, and for permeability, we use for horizontal permeability, most of the time we use geometric, and for harmonic, KV or vertical permeability, we use the harmonic averaging method. So they are different from each other. But at last, when you wanted, for example, a scale up the data, it's better to scale up it with different methods. For example, you have the data of porosity, you scale up it with arithmetic, and after that, look at the histograms. Look at the histograms of a scale up data versus histograms of raw data. And you do that with different methods. After that, compare those histograms together. For example, the histograms of arithmetic versus the histogram of geometry. So after that, based on those histograms, based on the output of those histograms, you can make a decision what averaging method you should use. But for permeability, especially for KV, most of the time you use harmonic because it decreases the permeability, and we know that the KV is much lower than KH. Yeah.
Okay, another question from Muhammad. Also, he is asking, what is the best upscale method for the permeability log?
Yeah, as I mentioned that for KH, horizontal permeability, we use geometric, and for K vertical, we use the harmonic model.
Okay. Another question from Muhammad also, but another person. What data will be required before static and dynamic reservoir modeling?
Okay, for well data, that's a good question. For well data, at first you must have the wellheads. You must import all of the wellheads. Wellheads tell you, for example, what is the easting and northing of the well, the coordinates of the wells. After that, you need the survey. Some of the wells are vertical. You should import, for example, you just insert the TD of the wells, but in the reality, they are not vertical. You know that when you drill a well, you have, for example, from the surface to the TT, you have some sort of difference between the easting and northing. So you must import the surveys of the wells. Also, you must import all of the logs. For example, you have the porosity logs, you have the also permeability. If you have the permeability as a log, or water saturation or density sonic for correlation. After that, you need some sort of, for example, if you have some sort of trends, for example, 2D trends, it's better to import those. And again, yeah, if you have geobodies from seismic and horizon from seismic, yeah, and also faults, you must import them. Yeah.
Okay. A question from another person. How can we use stochastic models in reservoir simulation?
How we can use that? The question was,
Okay.
Mr. Azam, how we can use
Yeah, okay. I'm not sure he's typing it right or not. He's typing, how can we use stochastic models in reservoir simulation?
it's not two model. Actually, it gives you, for example, the result, for example, it based on P10, P50, or P90. For example, it says that the probability you have this type of porosity is more than 90%. The probability of you have this permeability is less than 50%. That's a probability. So based on those, you make a decision. You have different cases. For example, you have a worst case or very high probability cases. So based on that, you make a decision. For example, you say that based on this stochastical algorithm, I have, for example, the average. I have average of the best case is I have 20% porosity for entire reservoir. But based on the worst case, I have 15%. So you will do the uncertainty analysis to see that how much based on worst case and based on the best case, what's actually your porosity and what's your how much actually oil you have in the reservoir, what's the oil in place, in the best course and in the worst course. Yeah.
The next question, how do you use import and use geobodies?
Yeah, in the geobodies, in the phase, you have a part of, for example, in the petrol, you have a part of, you have a module that is facies modeling. In the facies modeling, you must model your facies. And on that part, you have a different part in petrol, different module. You can use them, you can import them. And for actually when finally, when you model those, for example, geobodies, you can model the geobodies, and after that, you can use them as a trend, very good trend for porosity and permeability. So you have them, that's very similar, but for example, that's very similar, but finally in the geostatistical algorithm, it has different type of algorithms that work, actually most of them work with geobodies, but you have some sort of algorithm that better work with geobodies or creating a model with geobodies. So you have those modules in reservoir modeling software, you can model them and after that use them as a trend.
Okay, next question. Does a static model use seismic amplitude during property modeling?
I haven't used them. I just use the for the porosity. For the porosity, if you let me describe it in another way. If you have the attribute of the seismic you can import them. Yeah, you can import them and find them surfaces better. But for creating in other part of reservoir modeling software, really no. Just you can use the acoustic impedance for the trend of the porosity. For the as a secondary property, or for modeling the porosity, not much, but most of them is this type of work related to geophysicists, that they work on those, and it better shows the if they wanted, for example, extract the surfaces, they can better extract the surfaces of horizon, and they give you those type of horizon, but not as much as in the static modeling. We don't use them in the static modeling, just we use the geobodies, we use the surfaces, and also acoustic impedance for the modeling of the porosity.
Okay, because of the time, we will take two more questions. First one, what are the main factors influencing the final graphs model?
I didn't understand the question.
Okay, he's asking what are the main factors that affect the graphs of the model?
The main effect that it means that the main variable, the most important variable that affect the reservoir.
Maybe, or we can skip this question. Maybe it's not clear. So the last question is that do you recommend some artificial intelligence tools to support the duties of static and dynamic modeling?
Actually, I haven't worked in this area. I have no suggestion for that. I know that based on those, yeah, they create some sort of maps, but I think a software look like, for example, Petrel or Roxor software, they have all of the module and they can easily work with them, but I'm not sure about those because I haven't had a chance to actually learn this type of knowledge. I know that this is a new knowledge, but unfortunately I haven't any suggestion for this.
So thank you so much, Mr. Mansour, for your session. It's really amazing. Such an amazing experience in geology. Thank you again. Thanks a lot for all the audience for attending with us today. Last reminder for the feedback form and the certificate of this webinar. I will send now the link for the certification of the session in the chat. Also, another reminder for the upcoming course, which is static and dynamic modeling, reservoir modeling, which will start in the 25th of February, 1 month from now. The proposal for the course, also the registration form, all will be sent in the chat area, so please check it before leaving the session. Thank you, Mr. Mansour, and let's hope we meet again soon.
Thank you. Bye.
Thank you so much.